Hello.
Hello. Yeah, now it's good.
Yes. Hi, Manish.
Hey, Vijay. Yeah.
The Zoom is crazy. Zoom is crazy. It remembers from the website login. It doesn't use the app login.
Yeah, that's correct. Yeah.
We've lost Adam and TJ.
Yes.
TJ.
Tejas. Yes.
Tejas.
Yeah.
How are you doing, Niels?
Good. How are you, EJ?
Good. Are you back in Chicago now, or?
Yes, I am.
Okay.
Yes, I am.
So Niels, I can see your U Chicago T-shirt today.
Yeah, exactly.
Yeah.
Didn't you get one?
I got the white color. This time I'll come.
Oh,
I'll buy this one, the maroon,
yeah.
because
Okay, that's yeah. Well, this is the original.
yeah, this is the maroon is the original color. Yes.
That's all. That was 14 years as a director, and I only got this shitty T-shirt. That's all.
Is that a subtle classification problem there?
Yeah, right. Exactly.
The maroon class versus the white class.
So Niels, what you're teaching this fall?
This fall, I'm teaching Bayesian machine learning. So
And
it's pretty complicated stuff, actually. I'm struggling with it,
but what, like here you need to have like prior, and then you need to update prior using machine learning. What will it do basically?
yeah. I mean, part of the problem is with as we also have discussed is overfitting, right? So basically, what you do, you estimate parameters, and you use these parameters to predict with. But in Bayesian machine learning, the parameters are random variables.
Okay.
So you actually get a distribution over parameters, and then you can integrate the parameters out, so you completely eliminate overfitting.
Okay.
So you get something that only depends on the observations. So it depends on the model you choose. I mean, how many, if you take deep learning, how many layers and stuff you choose, but you don't. It doesn't depend on the parameters.
Okay.
So that's a really
That's pretty interesting.
yeah, it is.
But then, how do you solve? How do you solve for the? How do you solve for Neil? Do you use still approximate methods, or?
Well, I mean, you put a prior distribution over the parameters in, say, in a neural network, and then you use Bayes theorem to compute the posterior distribution, and then you can use the posterior distribution to integrate out the parameter. So you got a predictive distribution. It only depends on the observations. There's a lot of integration and there's a lot of math in it, so it's not particularly easy.
And I was wondering, like in your the Jupyter notebooks, there's a lot of functions which are not very easy to understand. So do you expect people to go through each function and understand exactly what they are doing, or you want?
Well, I mean, eventually people should be using. I mean, these because they're vectorized, they use the vector operations in Python, and that makes the code much faster. And so instead of using loops and stuff, we're using these vectorized operations. But it's a little. It takes some time to learn and get used to. But that's something you should always try to do in Python when you have something that's a lot of loops, and see if you can turn it into a vector operation instead. It's much easier. But that's what I've done. So now I don't expect people to understand all the code, but it does make it work a lot faster.
Okay.
Okay, should we
So we can get started. Yes, we can get started.
Okay. So let's see, I got my slides here. Okay. Does it show?
Yes.
Okay, great. So I'm going to just recoup a little bit what we did last time. Last time we had this example where we had a data set that could be perfectly separated by in a line. So I mentioned that and in this case we couldn't find a solution without regularization. So the gradient descent sequence, either just the gradient descent or Newton, does not converge in that case. So I mentioned that is a general phenomenon if your data set is linearly separated. So if you have a data set where you can completely separate it by some hyperplane, then the unregularized gradient descent sequence will not converge. And so I just wanted to show that this is a general phenomenon. So let's just go over this. So if we have an affine hyperplane, so that's given by some equation. It's a set of all x's in RD. So and vector in RD or point in RD can be described by its coordinates x1, x2, and up to xd. And the hyperplane is then given by an equation. Their coefficients, beta 0, beta 1, and so on, such that this expression, beta 0 plus beta 1 times the first coordinate plus beta 2 times the second coordinate, and so on, is equal to 0. So the hyperplane is a set of all vectors in RD satisfying this equation. And so if we have such a thing that completely separates the data sets, so here's an example. Here we have the red ones are labeled -1, the green ones are labeled +1, and they're completely separated by a line. A line is a hyperplane, affine hyperplane in R2, so they can be described with this equation here. So this is where D is equal to 2. But so I want to show that in this situation, there is no minimum for the loss function. So in general, let's assume we have a data set that is totally, that can be linearly separated. So this means that the points which have label +1, this expression here will be positive, will be bigger than 0. And for those points where the label is -1, this expression here will be negative. And that's simply because if you look at the logistic function, right, that is bigger than a half when this expression here is positive, and it's smaller than a half when when it's negative. And that's how we separate points using logistic regression. We look at this logistic function applied to beta times xi, and the logistic function, if that's the value of that is bigger than a half, then we label it +1. If it's smaller than a half, we label it -1. And that corresponds precisely to this expression here being positive or negative. So that means that what we have is that for all the points where the label is +1, this is bigger than 0. For all the points where the label is -1, it's negative, it's less than 0. So that means if we take this expression and multiply it by yi is +1 or -1. And when yi is +1, well, that's when beta times xi is positive. And so yi is times this beta dot xi tilde here is also positive. If yi is -1, well, that's when this expression here is negative. And so -1 times the negative thing is positive. So in any case, this means that this expression is always positive for all the data points.
Sorry, can I interrupt for 1 minute?
Please.
Yeah. So in the above two lines where we have beta dot x tilde, when it's greater than 0, I remember in the last slide, we said that this belongs to H plus, and when it's less than 0, that belongs to H minus.
Exactly.
And H plus was was linked to +-1 and H- was linked to +1. Why in the last lecture we had this flip notation?
I don't know. It's a good question.
Right.
Let's see here. If this is so, it's 1 divided by 1 plus sigma of minus this thing here. So this is yeah, no, that's yeah. No,
This should be
this is
+1.
correct here.
This is correct, I think.
This thing here is correct.
Yeah. Okay.
Okay, so the loss function, let's remember that what that was, there was this script L of beta is -1 over n is a number of data points, and then the log of this logistic function sigma of yi times beta dot xi. Now let's suppose we scale beta by some number bigger than 1. So if you just multiply it by something bigger than 1. Well, because it's yi beta times xi is always positive, you multiply it by something bigger than 1, well, then you make it larger. So that'll be larger than this one. So scaling it by something bigger than 1, they'll give us something larger. So that means that when the logistic function is an increasing function, the log function is also an increasing function. So log of sigma of this scaled thing here will be bigger than the original thing, right? So if you multiply beta, you make beta larger, then the log of sigma of this thing will also be larger. So, well, it's a minus. There's a minus in front of the loss function. So if these things are larger, then minus of them will be smaller. And so this means that the loss function of the scaled scaled beta, so mu of beta, is less than the loss function of beta. And so you can see that the loss function will just keep increasing because, of course, you can multiply by larger and larger mu here. So the loss function will just be decreasing forever. And so there's no minimum. It can't be. You can also see if you look at the gradient here, you can see that that will go to 0 because, again, minus yi mu beta, well, that will be negative, and so sigma of this thing here, as this goes to minus infinity, sigma will go to 0. So this gradient here will go to 0 at infinity. So when mu times beta becomes infinitely big. So it doesn't have a minimum because it keeps decreasing, and its gradient vanishes only when mu times beta goes to 0. So it goes to infinity. Sorry. So that shows that you can never have, you won't have a minimum for the loss function when the data set can be separated. So that's a general fact. So of course, if it's not perfectly separated, well, then there will be points where these things here do not, where this condition here does not hold, and so in that case there'll be positive and negative, and so that will turn it into a different situation where there is a minimum. So yeah, so you'll not find a minimum if you don't put a regularization in. If you put a regularization in, well, then you limit the size of beta. So you can't scale beta forever. You have to stay inside this thing that Adam drew last time, a ball or a ball in RD, and you have to stay inside of that, so you can't scale beta forever. So that was just
so again, one question. So this loss function which we derived, I thought this is derived for any kind of data set where the output is in terms of two levels, like label 1 and label -1. and then this is the what we got. So,
yes.
but we did never put a condition that whether they are completely separable or not separable.
No, no. I mean, if they're so this shows that if they are separable, then the loss function will not have a minimum. So we can't solve the problem without regularizing it, because the minimum of the loss function will be at infinity.
Right. So my question is like, what in that previous slide was showing that this only if they are separable, then this does not have a minimum, because I thought this loss function is a general loss function for any.
Yeah. No, but the thing is that, so what you have is that if it is separable,
yeah,
you have this condition here for all data points.
Oh, I see. Okay.
You only have that if it's separable.
I see. Okay.
So if it's not separable, then you will have some where this is positive, but you also have some where it's negative.
Correct. Oh, I see. Okay.
So that will change the picture. So let's go on to a more advanced model, and so that's what's known as support vector machines. And support vector machines is actually a fantastically elegant model, and it for a long time it was really the preferred model. It's very flexible. You can solve a lot of problems with it, but it does not scale so well when you have very large data sets, and then the computation takes too long, and so it is not for billions of data points. It just doesn't. You just can't do it. But it's a very, very nice idea, and it's for small data sets. It's absolutely great. So let's look at a somewhat complicated data set here. So you can see this is definitely not linearly separable. That this is you can't find a line that separates these two, the purple and the yellow things here. So we can try logistic regression. So here so this code I have uploaded. You can look at this code. So the piece here is sort of a way to visualize this decision boundary. So the one that separates the plus ones and the minus one labels. So the model is going to predict points having a label +1 and other points have predict -1. And this code here is going to sort of show where it separates the 2 points. So let's run this logistic regression on this data set here and see where it separates the two, the +1s and the -1s. So you can see here that it misclassifies quite a few points here, right? So we have so the purple area here, that should be the ones that have all the yellow or orange points in it, and the other ones should be on the blue point should be on the other side. But you can see here there are a number of points here that are misclassified. These yellow points here, they belong down here, and these blue points here, they belong up here. So but that's just because of course it can't be separated by a line. But the logistic regression tries to do the best it can, and so let's try to figure out how well it does and see how well it does how well it separates the data set here. And we can see that if we run these metrics here, so these are part of the sklearn metrics as an accuracy score and a confusion matrix. We haven't discussed confusion matrix, but I'll do that another time. The accuracy score, well, it simply looks at how big a percentage of the data points are correctly classified by the model. And so it correctly classifies 89.5% of the data points. So that's maybe you think is pretty good, but actually it's terrible. So that's not good. So when you're using these things, you really want much better. Yeah, so it's just the accuracy score compares the. So now let's try this more advanced thing, the support vector machine. And I'm going to use a support vector machine with a radial basis function that we don't know what that is, but we'll We'll see what it does later on, but it's a way to, again, a classification algorithm, and again, you can use the code here. And again, I have this code here, which gives us the decision boundary. It shows how it separates the points. So let's see what that does. So here is the separation boundary for a support vector machines with an RBF kernel. That, as you can see, is not aligned anymore, and it does pretty well separating the point. We can't separate it completely without really overfitting. We probably could get a by sort of tweaking the parameters in the RBF in the support vector machine, what's called a kernel. We could probably get it to separate these almost perfectly, but that would be total overfitting also. But let's see how well it does in separating these, and we can see it does about 5% better. So it's well, 5% is maybe you think that's not so much, but it's actually huge. It correctly classifies 94.5%. So that's a much better thing. So what is this support vector machines? Well, it's a as I said, it's a very, very elegant model, and we will start with describing what a linear support vector machine is, and a linear support vector machine that will also create a separation line. And so here is a linear SVM, and see how well that separates. That does about as well as the logistic regression, but it's, as we'll see later, much more flexible in terms of generating much more complicated decision boundaries. So what is this? What is this support vector machine? How does it work? Here is the code for the linear support vector machine. We can see the accuracy score is better than the logistic regression. It's 86.5%, but of course not as good as the one with the RBF kernel. So the principle in the support vector machine is to find the best, in some sense, line that separates the data. And so here I have my data set here. I have the -1s are red, the +1s are green, and I have 3 lines that separates them. So which one is the best line? I could make that a quiz, but I didn't. But I think we can somehow agree that it's. Well, what would you say would be the best line?
I would say my vote is for green line.
Yeah. Okay. Mine too. And why is that?
I would say because it is very cleanly separating the green points from the red points without touching any point very closely. So even if they're like more data points around that point, it will still separate well.
That's right. Yeah. See, the thing is that you can sort of put a band around this. I think it's in the next line. You can put a band around this green line where there's no data points, right? You can put a belt around it, and so that there are no data points inside this belt, and so that's the widest belt you can put around. You can put a belt around this yellow one here, but that'll be very, very narrow, right? It'll be very close to the lines itself. So there will be a.
So is it more precise to say that the green line is the one that maximizes the perpendicular distance of all the points to it?
It's the one that maximizes the distance to the closest points.
Oh, just the closest ones.
Yeah. So yeah, it's just the closest. So that's actually the idea. We're going to try to find this line that has a property that this band around it is as wide as possible. It means that the distance to the closest data point is maximal. So for instance here, what's the distance to the closest data point? Well, that's this little distance here. The distance from the green to the closest data point, well, that's this distance here. So you see, that's bigger than for the yellow one. The same thing for the green one here. The distance to the closest data point is this thing here. But again, that's smaller than for the green line. So the green line is in that sense the best separation. So the idea here is again to look at the distance to the closest point. And so it's sort of the line, the best line is gonna be right in the middle of these closest points here. So here we have a point here that looks like I have more or less pretty much the same distance as this one. So the line here will sort of be right in the middle of these closest points. And that has to be expressed mathematically. And one can do this in a somewhat complicated way. But let's. I don't want to. I think Adam has quite a bit of material, so I'm not going to go through the whole thing here. But let me maybe go up to the board and try to explain a little bit what we're doing here. So I'm going to not stop sharing and show the. So can you make my picture big, Manish?
Yeah, I can see your board. Yeah.
Yeah, but I can't see. Can you? Is it big?
Yeah, it's big. Correct. Let me pin your video so that's big. Yes, now it's perfect.
Great. Yeah. So I made this drawing here on the board here, and so this is pretty much the same as what's in the note here. So here we have this distance here to the closest point. Here we have another one of the points that are closest. So how do we express this mathematically? And so how do we use this? How do we find this line here? So this is the sort of the line here, the separating line we're gonna try to find. So the idea is that again, a separating hyperplane is given by equation of this form. And if we look at the same line here, but look at it through the origin. So the origin is here. So here's my x2 axis and here's my x1 axis. So the origin is here. So if I try to look at this line parallel to this line here, but through the origin, what is that given by? Well, we can describe that as all the vectors that are, all the points that are perpendicular to a given vector here. So this line here, we call that L0. So that is given by an equation of this form, beta 1 x1 plus beta d xd equal to 0. And so when I'm going to move this line here, I'm just going to add some constant term to it. Well, I can simply say that this line here, L0, is the set of all points of this all the set of points in RD such that beta dot x is 0. And that specifies the set of points that are perpendicular to this vector here. So this is all the vectors here that are perpendicular to B. And so in order to get up to this line, I just have to parallel translate it. That means I have something like L0 plus some vector B is equal to, well, that'll be L1 here. And so what is L1 here? Well, that'll be things of this form. It'll be some point x1 up to xd, where this point is in L0, and then plus some vector b, and that just means adding some component to each of these, so that'll be something of the form x1, x1 plus b1, and x2 plus b2, and xd plus dd. And so how can I describe the L1 here in terms of beta? Well, if I dot this with beta, right, you can see here, if I dot this with beta, the first one here would be 0, and all I'm left with is beta plus b. So if I dot this with beta here, I just get beta dot the vector.
Hey, Niels, can you use on the left side of the board, because that's not visible. So left side is clearly visible, all of it. Yeah, okay, perfect. This looks good.
And let me call this this C. So the line L1 here is just the set of points satisfying the condition that the beta dot z is equal to this constant c here. So that's how I can describe this. I can describe a line. So a line not necessarily going through the origin, or in this case an affine hyperplane, not necessarily going through the origin. I can describe this as it's all the points such that there's a fixed vector beta such that all the points here satisfy this equation. Beta dot c is equal to the constant, some constant c that's part of the equation. So in order to find this line, or this hyperplane in general, what I have to do is I have to find this beta, and I have to find this c. So we need to find beta and c, and such that L1 is equal to the set of z and b, such that beta dot z is equal to c. So that's my first step in order to try to find this line here. That's to be able to write it in this form here. And then I need to find beta and z. So let me see. I have a point here that's the closest. One of the points where the distance to the line is minimal. So what is that? Well, I measure it by looking at this line here that's perpendicular to the line L1 here, and this will be my distance to the point here. Let me call that mu. So this point here, let me call that x. So there's a point corresponding to x here on the line here. Let me call that a. And so I have my little vector here going from A to X. And so that little vector here, we can call R. That's the one that has length mu. Now what is this? What is this little vector here? Well, this is R is equal to X, this vector here. And here I have the vector A. So this vector here is X minus A. So what can I say about this this vector R here? Let me erase some of this because now it's getting a little crowded. Yeah, so what can I say about this vector R here? Well, this vector here is perpendicular to this line here, right? It goes from it's a perpendicular distance here, so it's perpendicular to mu here. Now beta is also perpendicular to this line here. So that means that these two, well, they're both perpendicular to the same line. That means they must be parallel. So R must be parallel to beta. So in vector length, well, because they're both perpendicular to the same, in RD to the same hyperplane, in R2 the same line. So this means that R is a multiple of beta. And so U, the length of R, is just gamma times the length of beta. So R was X minus A. So if I take beta and dot this with R, well, that's the same as beta dot with X minus A. Now, X, well, X is here, but A is on the line L1 here. So that means that the A is one of these points here satisfying this equation here. So that means that this must be equal to beta dot X, and then beta dot A is C. So this is just minus C. So we get here R is gamma beta dot R is equal, let's starting this with beta, let's give me gamma times the length of beta squared. And so I get well, so this is mu is the actual value of gamma times beta. So this is if I take actual value here, this is equal to the absolute value of gamma times, it's the absolute value of gamma times the absolute value of the norm of beta squared. The absolute value of gamma times the norm of beta was mu, so this is equal to mu times the norm of beta, and so I get the equation that mu is equal to the absolute value of beta dot x minus c divided by the norm of beta. So what I then have is that all the points here, all the other points in the data set, well, they're further away than this point here. So if I take a point here, so it's I here, so they'll be further away than this. So again, the distance here, well, that would be again on the same form here. So we'll get that beta dot xi minus c divided by the norm of beta will be bigger than or equal to mu, because that will be the distance from here to any of the other data points. So we get a that for the points that are closest by, this is equal to mu. For those that are further away, it's bigger than or equal to mu. And now I will I'll go through all the computations because it's spend too much time on this. Maybe we'll go through it again next time. But basically, what you do is you can scale this. So the equation here was that mu times norm beta is equal to beta x minus c. That's the value. So if you scale beta here, what happens if you scale beta? Well, that just means you move beta here, and you make, or you don't move it, but you make it shorter or longer, go in the other direction maybe. But you can of course multiply beta by any scalar and still get the same line here. You get the same line from the origin, but you will change the c. So we look at lambda times beta instead. It'll still be perpendicular to this line, but the L1 here will be the line satisfying this condition here. So that would be L1 will be equal to the set of points satisfying this equation here. So the idea is that by scaling beta here, by multiplying by an appropriate scalar here, so that in this case lambda will be 1 over mu times the norm of beta. So if I scale by that, what happens is that this becomes 1. And let's say that W equal to lambda times beta. So this lambda here, then I get the equation 1 is equal to, and then here for this point here, I get beta x. I get W x minus lambda c. And for the other ones, I just get something that is bigger than this. So W dot xi minus lambda c will be bigger than or equal to 1 for all the other data points. So what do I have here? Well, I have that so what do I want to do? I want to maximize mu. I want to maximize the minimum distance to the closest point of the data set. So what does that mean? Well, mu times norm of W is equal to 1. So I want to maximize mu, that means I want to minimize the norm of W. So finally, the process, or the whole thing comes down to minimize norm W subject to the conditions that W dot xi minus lambda c is bigger than or equal to 1 for all points in the data set.
Sorry, Niels, I missed one part. How are you getting mu times norm of W equal to 1? Where did we get that equation from?
Because I multiply, so I take W equal to lambda times B.
Okay.
So I multiply B by this this scalar here. So that means if I have here I have mu times the norm of beta.
Mm-hmm.
So when I scale by this, when I scale B by this number here, this becomes 1, right? So this is
okay.
Mu times so it becomes mu times beta divided by mu beta.
Okay. Yeah. Okay.
And so this thing here is what I call W.
Okay.
And so this then is now an optimization problem. It comes down to minimize W squared, minimizing norm W and norm W squared is the same, subject to these conditions here. And I can rewrite these conditions here by putting in the labels here. yi W xi minus, and then two prime here is bigger than equal to 1. So this is just to get rid of this absolute value sign here. I can arrange it such that I have the positive sign when I'm at label +1, a negative sign when I label -1. So in any case, yi times this thing will be positive, and so bigger than equal to 1. So this is an optimization problem, a convex optimization problem, which can be solved. But I will go through this in more detail next time. I won't go through how you actually perform this optimization, because that requires somewhat advanced models, but somewhat advanced math. But I'll write out what it means, and then we'll take it from there. But I will let Adam take over, because I think Adam has quite a lot of material. So I'll return to this next time. Okay, Adam, you're on.
Oh, thank you. Okay, so I'm going to share my screen. Which do I want to share? Gosh, give me a second here. I don't have the right thing up yet. I do. Okay. Sorry for this. Okay. So, after Neil's theory, I want to go back to some of the practical stuff and practice applications of this. And in particular, last time I promised you something about Lasso that was a little more interesting. Now, so the main goal of today is to take some data from scratch and see what we can do with Lasso with it. So what we're going to do here is actually go through how you would attack a problem. So we're going to talk about how you build the models and validate it. And in the end, I don't think I'll get to it all today, but we're going to talk about logistic regression, ridge and lasso. And this is an important point. Do not expect spectacular results. So one of the problems I think with many machine learning classes is you take the standard data sets and things always work out really well. That doesn't always happen. It usually doesn't happen quite so easily in the real world. So I want to download some data, stock data, and I'm going to ask, can one predict whether a stock will move up the next day? And that's really an open-ended question. So the first thing you have to do when you have a question like that is sort of get it into something that's a reasonable question, something concrete you can answer. And the concrete question I decided to ask was, given the past 5 days versus the closes of the stock and some technical indicators, can we predict whether or not the stock is going to move up more than 1% in the following day? So that's a concrete problem. Now, okay, so quiz. What's so special about up 1% after 5 days of data? And the two choices are nothing, these are arbitrary. 2, everything is perfect, it would be a waste of time to do anything else. So that's the first quiz. That's the wrong one.
It's the wrong one? Okay, sorry.
No. Well, how many people do we have? Maybe the people can just chime in.
Yeah, they can just speak up. So, sorry, what's the question? Adam, can you repeat?
So the question is, what's so special about using the decision of we're going to try and figure out a model to predict whether stocks will be up after 1% by looking at 5 days worth of data? And the two choices are nothing, these are arbitrary choices, and 2, these are the perfect choices, it would be a waste of time to do anything else. Manish, you're unmuted, what do you think?
Yeah, I think the 1% is a reason that if we are assuming that the returns are normally distributed, then we are expecting that this is more than 3 standard deviation move, and we can estimate what percentage of time this will happen, probably.
Well, I don't disagree with anything you said, but those aren't the two choices. The question is, is this a good choice or is this an arbitrary choice? Is this the only choice?
Oh, sorry.
It's an arbitrary choice, I think.
Yeah, I think it's an arbitrary choice.
Absolutely. And the point is that, okay, sorry. There's nothing particularly special, but you have to pick something. We'll see. I want to say well, I don't want to say, but it's this 1% is certainly not a 3 standard deviation move or anything like it. So how did I decide to do this? So I use something called the QuantMod package in R, and so you just install that package as QuantMod. And when it does install, it'll install 2 other very nice programs called XTS and TTR. XTS stands for Extensible Time Series. It's a package that allows you to do with time series the kind of ordinary things you might want to do with an ordinary matrix, pick columns, select rows. It stands for Extensible Time Series. It's the most general and flexible time series package in R. And TTR is a collection of technical indicators. And if you want to use technical indicators, it's great. And in particular, it makes computing any sort of running average or running mean or running standard deviation, a one-line operation. So it's very, very nice. And QuantMod, among other things, allows one to download data. Excuse me. Sorry. Here we do it. So I just want to show you this. And I've had some discussion with Niels about when you tell somebody you're in a class, you think that they would do better than to reply, whoops. Anyway, as of Labor Day, the get symbols was working in R with, and what this allows you to do is to download a series of stocks. I just load the library and it suppresses messages, but I can't suppress warnings. So what I do is I give it a start date and an end date. So I'm going to get all the stock data between January 13th, 2008 and 2012. Why those dates? Not particularly, pretty arbitrary. It's another arbitrary choice I made. And I chose IBM. Why? Why not? But because I wanted to do this many, many times and I didn't want to, query the server every time and wait, I did save the file. And then I just, as an RDS file, just a thing, and I just was reading the file and question?
No.
Yeah,
Okay.
I mean, it used to be that you could put in an arbitrary list of symbols there and
You
get
still
the,
can.
what?
See where it says tickers equals this?
But
If I just would have used a bunch of symbols separated by commas, it would have worked just as well.
yeah, the only problem is that Yahoo don't let you do that anymore. So they will not let you automatically download it.
The same would work just fine.
No.
It did work. I mean, for 2 stacks anyway.
Yeah,
right.
but they won't let you. Yeah, right. It used to be you could get a whole all 500 stocks in the S&P 500, but you can't do that anymore. So they have decided that data is very expensive. So too bad. But one stock you can definitely get, maybe 2.
I've always been told that you can get as many as you want. It's just a question of pausing it. But it's true. I haven't tried that in a good 6 months.
Yeah, no.
Okay. I'll ask. So I got this time series object IBM, and you could see, just if you wanted to do more with it, it gives you the open, high, low, close, the volume, and the adjusted price. That's the price adjusted for dividends. We won't be playing with that. This is a little low tech. So one of the nice things is QuantMod has a very nice charting package. So this is the absolute, plain vanilla make a chart of IBM. And you can add various kinds of things like Bollinger Bands with this very simple thing, and you can do that. So if you want to look at the data, it's a nice package to allow you to inspect stock data. Okay, so we want to predict if IBM is going to be up more than 1%. And from the data we had, it's not clear what to do. So I did say we're going to just use the close. So I just want to get the close, but I also want to get the previous 5 days close. So we need to create a frame, a matrix, if you will. Each row will have 5 days of data, and a 6th column that will say yes or no for whether or not it went up 1% on the 6th day. So how do we do that? So I only want the close data. So the first thing I do is I take that. And I want to create, a matrix with 6 columns and has all the data, and I do that. And I won't go through the arithmetic logic, but if I start with I equals 5, or actually 6, this will do it, and it will give me all the data. It'll give me the 6 columns, and I'm going to keep the volume data too. So I'm going to collect that. Now, the only thing is I don't want the volume from the day ahead, so I have 1 less columns. So I had 6 and 5 and 11 columns. I don't know why that came out boldface, but the last thing is I bind the 2 data frames to create a new data frame just called IBM.data. And if you use cbind.data frame, it's quicker than using just cbind. So I think I've covered everything. We get our data. And we just put it all in a big matrix with 11 columns. Once it's that, it's a useful feature that you can create a data frame from this. Now, data frames are nice when you have big matrices with lots of columns because you can give the columns names and you can call your data by the column names. This just makes life so much easier. It also means that if you add more columns and you move them around, you don't have to remember what, whether the thing you wanted was column 21 or column 22. You just have to know what it was. So I make my data into a data frame. I give all the columns names, D1 through D6 for day 1 through day 6, and V1 through V5 for the 5 days of volumes. Now, we're interested in whether the returns on day 6. So I look at IBM on day 6 divided by IBM of day 5. And then I'm going to change that. All I want is it to be 1 if it's bigger than a 1% move, and 0 if not. So there's this very nice function, if else, that allow you to create binary variables. I think I've mentioned it in a previous talk. So if else, I look at this delta, if it's bigger than 1.01, that means it was a 1% return, you give it a 1, else you give it a 0. So once you've done that, you can see that if else, gave the delta mostly values of zeros and some ones. Okay? So, and as I write at the very bottom, the logic of if else is, if else, you give it a test, and if it passes the test, you give it a certain value. If it fails the test, you give it another value. Okay, so del takes the value 1 when there's at least 1% move and 0 otherwise. No, did this thing in the wrong order? Okay, so quiz. Based on the above, so the above is right here. I've given you a summary of IBM data.delta. So what it does, and the min, the first quartile, the median, the mean, third quartile, and the max. What percentage of the moves were 1% or higher? Okay. I'll give you a hint. You can read it off of this data table. Any guesses? Niels, any thoughts?
0.
Okay. Well, the answer is about 25%. And this is a good example of, when you have data reading it, the mean is 20.22, which is about 0.25. So del takes the value 1 when there's at least 1% move and 0 otherwise. So the mean of del is going to be the number of ones divided by the number of rows. Or in other words, it's going to be the percent of ones. So, this means that about 22% of the time there was a 1% move. So, Manish, I don't think this is going to be a 3 standard deviation move.
Right.
If you expect to occur about 1% of the time or so. So, this is the kind of, and by the way, none of this is at all complicated, but some of this took quite a while to get straight because that's the nature of when you're given a raw data set rather than a data set that everyone already knows and has been put in the right form already. Okay, so the other thing is we have 11 columns now. We have 10 we're going to use for prediction, the 5 days of data and the 5 volume. Question? Nope. Okay, so I want to create some more. I want to look at percentage changes over those 5 days. Those should be useful. And I want to get some technical indicators, moving averages, means, medians. And then we're going to take some logarithms. Why logarithms? Why not? One of the logarithms tend to be more useful than a priori one would have a reason to think they should be. So sometimes taking logarithms are good, and it can't ever hurt. Now, to do all this, I'm going to do what's called attaching a data set. I'm going to attach the data set to the environment. This means that you can call variables just by their name. You don't have to use the $sign notation or the dot notation of Python. But really important thing when you attach data sets is to remember to detach them. So when I do this, I will write the attach and the detach statement at the same time, and then just put the code in between the two. So here we go. So I wrote attach IBM.data, detach IBM.data, and then I just created a bunch of new variables. So these D sub like 4.2 is D4 divided by D2. These are returns over different periods of time. Question?
That's good.
Sorry?
No okay. Question.
And then I took some moving averages, smooth moving averages. I took from the 5th day to the last day. I took 5, 10, 23, and 45 days. I took running mean, 5-day mean. I took running medium, 5-day medium. So for every day, I got the medium over the previous 5 days, mean over the previous 5 days, and 5, 10, 23, and 45-day moving averages. I found some indicator called momentum, and I did that for a few days. And then I took relative strength indicators, which is another reasonably well-known technical indicator. So I wound up with a lot of things. So one point I want to mention, when you do these things, particularly these running things, what it does is it defaults giving you NA for the periods before when it has enough data. So when I take the smooth moving average of the 5th day for the 45 days, for days 1 through 44, this returns the value of NA. It only gives you a real value when you have 45 days worth of data. So what this means is if you want to avoid NAs, you're going to have to lop off the first 45 days. But we'll get to that later. Logarithms.
So Professor, what does momentum do? Is it like increasing or decreasing sequence, whether it's
it's a momentum measure, exactly. So I don't use a lot of technical indicators and never did when I traded. Nothing, things like momentum or RSI. They're a little too long term for the kind of things I did. But I think for a project like this, per se, you don't have to know what they mean. I mean, honestly, if I was going to do a more serious study, you certainly want to see, for example, you'd want to run correlations. You might want to chart things. You might want to have some idea of the ranges. But, you know, that there's some sort of useful number is enough at this point. One of my fantasy projects is to run a long-term study and find all the relationships between all the a large number of technical indicators and find a minimal number of them that really suffice in many cases. So, and now we're going to do logarithms. Now, remember, logarithms only make sense if your numbers are greater than 0. So, and no NA. So we have to deal with that. So I cropped the data set. I removed the first 45 entries to make sure I didn't have any NAs. And IBM did positive. If you look at the columns, these are the columns of the, just the 5 days, and these are the volumes. So this is really all you want, enough anyway. And so then L applies, it says it's list apply. So it's applied to IBM.positive, the log function. This will column by column give you the logs of go through all the columns and just give you the log of the columns. And L is data frames under the hood are a list, and this is just the right way to do it. But then it gives you returns a list, and you need to return it to a data frame. So, excuse me. I've often complained to Niels about, you know, sort of extra stuff that Python makes you do. This is the R version of my complaint. You know, the L apply will take a data frame and return a list and not a data frame. But
say that again.
I said, which part?
I'm going to defend Python to the death. What are you saying about Python?
I said something good.
Oh, okay.
I said that, you know, I complained to Niels about, you know, Python things that are, you know, unnecessary and annoying. This is an R example of that.
Oh.
And, you know, that I'll apply and then you have to turn it back into a data frame is, you know, something annoying in R. I'm trying to be fair here.
It's not the only example.
No, it's not the only one, but there's at least 1 or 2 others on the list. Like the Python list.
So you can't apply a log directly to a data frame and get a data frame.
No, you have to hit data frame again.
I see.
Very annoying. It's nearly as annoying as having to write np dot, you know, a million things for obvious things. Anyway, and then I just get the column names by pasting log in front of I just found the column names and I just added log to them and then that. So I just have column names for everything. You know. So this is a large part of what you do. So why didn't I take log of D21, etc.? And the real question is how many distinct numbers are there in log D21 and log D32? And the heart of the question is that 3 numbers, 4 numbers, or 2 numbers? And the hint I gave you is that log of D21 is the log of D2 minus the log of D1. So the point is this is going to be the log of D2 minus the log of D1, and this is the log of D3 minus the log of D2, but you got the duplicated log of D2. So it's really three distinct numbers, the log of D1, the log of D2, and the log of D3. So, you know, when there was no need to take the log of the returns when I already have the log of the dailies. Okay? So even though I didn't take any log returns, tacitly they're in there because I do have the log of the outrights. Okay? And here I wrote out that the reason you use lapply is it's much faster than doing the ordinary apply. And so what do we want to do in the end? We want to see if we can predict whether data is up. So we are going to have to get out of our data set. We have these two variables, the 6th day and this delta. That's the information. Predicting whether delta is going to be 1 or 0 is kind of easy if you already have delta in your information. So I need to remove it. So I make the y variables. I just create an index to say which columns are in D6 and delta, and I let the y variables be those, and then the x variables be the opposite. Now these are data frames, and some things want data frames and some things want matrices. So I just called x and y the matrix versions of this. So x is basically all the data you have, and y is the dependent variable, which is 0 and 1 that you want to predict. And all the work we've done so far was, you know, the kind of thing you're going to have to do time and time again if somebody gives you a problem and say, what's the answer? Okay. Let's see, I duplicated it. So we've got to get the data ready for usage. And by this, I mean, we have to create, train, and test. Now, remember that the best way to, and the way you should always use if there's enough data is the train test model, which means you separate your data into two pieces, a training set and a test set. Okay? We only use training data to train the model. You do not, you put the test set away. Only after you are satisfied that you have a good model, you show it to the test set, and its values on the test set is going to be your best estimate to how well the model is going to work on new data, because it is new data. Okay? Now, maybe for Manish, I'll mention, you know, there's all these discussions about, you know, when you have time series, you have to be careful not, you know, to not look forward. But I really don't think that's relevant in a case like this. First of all, there's a lot of data, and the patterns you see recur time and time again. And I've thrown in enough variables to distinguish them. So my feeling was that it was reasonable, actually, in this case, to just randomly sample the data and not just sample up to a certain period and then test on the post period. I mean, I really think in some sense, you'd like to believe that if you have 5 or 10, you know, sequences of dates and their returns, you know, that should be the information and it should stand on itself. But
I will comment, like, probably what we are doing, probably these are simple indicators. A lot of people can try these simple indicators, and if they see the pattern and if they start trading, that will go away. So it's still dividing the data in a temporal horizon will make sense, because if we do random, we think that it will still is useful, and probably it's not anymore because it's arbitraged away.
that may occur, but that's kind of a meta level. Right. But in any event, I do have 2 years worth of data or 3 years worth of data. So if I sample through over 3 years, that kind of arbitrage is going to go away anyway. Shouldn't be enough of it to do that. I have about 4 years worth of data, I want to say. Anyway, we could see. I'll be glad to do it a different way and see if we get different results. So I did sample this way. I created train and test for the X and Y variables. And the only important thing is you create the sample set, and you let your training set be X on the sample, and the test is the non-sample items. And you use the same thing for Y, same sample. And now we're going to use Lasso. And I'm going to use this GlimNet package. The point of the GlimNet package is it has an extra parameter, alpha, and it penalizes coefficients according to a certain percentage of the L2 norm and a certain percentage of the L1 norm. And interesting, so if you don't tell it what you want for alpha, it defaults to 1. And if you let alpha equal 1, this term, first term, becomes 0, and you're just left with the L1 norm. So the default is to do Lasso. Okay, so I loaded the GlimNet package. And once you've done that, the command to load the data and create the model is very simple. Function is called GlimNet, and you have to give it the training data and the independent dependent variables. A little aside, according to the notes for the package, if you want to do logistic regression, which is family binomial, you want y to be a factor. It doesn't want to be the number 0, 1, it wants to be 0, 1 factors. And if you want to do reg, it's essentially the same thing, except you have to tell it alpha equals 0. So just to, and this is very quick, but let's just plot this. Now, this is a typical output from some model, but you can't see anything because basically we have too many coefficients. What this is showing is as the L1 norm increases and the penalty goes in, more and more variables are becoming 0. And ridge is similar thing, but it's even more. See, the advantage of Lasso is that some of the coefficients and whatever they use for the plot are going to be 0. All right. So, as I said, that is interesting because, yeah.
Adam, in the previous slide, as we are increasing lambda, then the m is becoming smaller. So the coefficients are still why the red line is becoming bigger and bigger. This is.
I think that's the only one that's going. I think all the others are becoming 0, or they're going towards 0. The other thing is maybe it's confused just because of the scale.
And even like this black line, there are like few lines at the top, and this red line, they are not. They continue to grow with even with the bigger lambda.
It's just a scale question. If you go big enough, this line has to eventually go there.
Okay.
It just is. Okay, so those are very interesting. And the more interesting question is, remember you have this parameter lambda, which is how much of a penalty you're going to do. So, I mean, there's infinitely many choices, and this is what's called a hyperparameter, as we've discussed. And so you want to find out what lambda works best. And you do this via the function cv.crossvalidation.glimnet. And what it does is it uses cross-validation to find the best lambda. So the default is to do tenfold, but you can make it what you want. So what do I mean by it uses cross-validation? It goes through a range of lambdas, and you can either tell them which lambdas you want, or it'll make its own choices. It has an intelligent system for deciding what's an appropriate range of lambdas. And then in its grid of lambdas, for each lambda, it divides your data into 10 pieces. And it trains the model with that lambda. So it gives you a specific set of coefficients on 9/10 of the data and see how well it predicts. It does this 10 times, each time emitting a different 1/10 of the data. At the end of the day, it has those 10 estimates based on the 10 different models it created, based on the 10 different partitions, and it averages them. And that gives its estimated error for that particular value of lambda. It goes through this for a large number of lambdas, and then it comes out with the one that's the best. Okay? So the form of this is cv.glimnet, and you just give it the data. And this plot, by the way, so this is a nice plot. I find this very interesting. What it shows you is, it's actually looking at the logs. So these are so this is like 10 to the minus 9, 10 to the minus 7th. It's showing you how the mean square error changes for different values of lambda. In case you're wondering what that line is, obviously this one down here is going to be the best. But what this is saying is there's a lot of people who like to use the 1 SE rule, which is you take the best value that's within 1 standard deviation of your minimum. So that would be this one. I don't want to get into that right now, I can, unless anyone wants me to. But I use that one, which is the minimum one. And it's that.
So this is the error over the different cross validations.
Yeah, over the sum of all the 10 cross validations.
Okay.
So the first thing it tells us is the value of lambda we want to use, both numerically, or we could just always say CV fit $ lambda dot min. What this means is the penalty on the coefficients it's suggesting is going to be rather small. So, but we'll see it does do that. So if lambda is small, the penalty on coefficients is large or small. What is the penalty if lambda is 0, which is really small?
I mean, there will be no penalty if lambda we put as 0.
There'll be no penalty if lambda is 0. So if lambda is small, the penalty on the coefficients is large.
Yeah.
Right?
If the lambda is small, the penalty on coefficient is small, right?
It means that the coefficient can still be pretty large without being much
Correct.
of a penalty.
Correct. Yeah.
Okay?
Yeah.
So, how well does this predict? With R, there's typically a predict function. So I use predict. I want to predict with the model of Lasso. And my data, my X set is going to be the training set. And the type is response, it's just what it is. And that will give you the probabilities. And S is the value of lambda it chooses. They have some reasoning. I don't understand why they don't use lambda for that parameter, but S is the lambda that they're going to use. So I just use the minimum value, and you can see it's predicting things. So the first thing, it says essentially 0 chance of it being up 1%. Of the first 6 days, day 3 was the biggest with a 40% chance of an up move. Okay, so what we really want to use is, we want to know a 0 or 1, and we could use round, or alternatively, instead of using response, which gives you the values, the probabilities, you could use type equals class, and then it gives you 0 and 1, but it gives it to you its characters, so I just make it a number 0 or 1.
Can I ask, how does it compute the probabilities?
Sorry?
How does it compute probabilities?
It's doing the same thing that Python does. It's just computing a penalized model for the
So this is
regression.
It's not using what model is it using? A logistic regression model here?
Yeah.
Oh, okay.
It's just using a logistic regression with a lasso penalty on the coefficients.
Sure.
This is all we're doing. Is as you asked, I did a prediction problem, so we're using a logistic regression rather than an ordinary regression.
Okay, so Adam, here when we see the head of y.pred, these are, how do we know this is a good prediction or bad? These are the cases where we actually had 1 and we got the probability of 6%, 7%, 40%.
So Manisha's question is, how do we know whether these predictions are good or not? And that's the next slide. Okay. So, I mean, we like it if for all these predictions, in fact, none of these were up 1% days, that they were all 0. Now remember, we know what the answer is because we do have y.train.
Right.
So,
Professor, how do we interpret that results attempt? So is it showing us the probability of having a 1% increase, or?
Yeah, that day, the next day. Yes, that's exactly.
But so we're using logistic regression. It's gonna take if this is bigger than 50%, it's gonna say 1, right?
Yes.
Right, standard logistic regression. You know, the standard thing is to say, well, if the probability is bigger, 50% or bigger, we call it a 1. Just doing class just does it for us. You could accomplish the same thing by using the round function, for example. Which round of a number is 0.5 is 0, and a number between 0.5 and 1 becomes 1. Okay, so we can see how well it is. So Niels gave the confusion matrices, and in R there's just a general table function that allow you to compare things. So we can actually see the training value of 0 and 1 and the prediction value. So they agreed mostly that it was when it was 0 and 0. But if the training value was 1, it predicted 0 85 times and 1 61% of the time. So you know, that's what it is. You know, it's better than, so it's 140, so 20% of 140 would be about 30. So it got about double right than what it could, than just random guessing.
Maybe I didn't say what the confusion matrix was. So.
Oh, I thought you had used it. Now. Okay.
No, I skipped it because well.
So what a confusion matrix is it just tells you, you know. So this is the training labels and the prediction labels. So if the training label was 0. It predicted 0 534 times, and it predicted, so if the right answer was 0, it predicted the correct answer 534 times, and it predicted the wrong answer 20 times. This means train was 0, but it predicted 1. If the training label was 1, it means it predicted 0 85% of 85 times, and it correctly predicted 1 61% of the 61 times. I keep trying to say percent, that's not correct. Okay. So this gives you a breakdown of how well the model worked with a 50% probability. Now, as I said, just, you know, see the past, it was like 22-ish% we know were 1s. So this is a little bit better than twice as good at just guessing. You know, it guesses 1 correctly about 40% of the time. It's overwhelmingly good on predicting not up, but that's the much easier prediction. Okay, if you want, I can just repeat this again, just, you know, to give people a chance to grok it. Okay, so the question I was asked on the last slide was, you know, all right, we have these predictions, were they right or not? So I can get a, you know, I have my prediction, so these will all be prediction 0. But I could also say, ask what are, you know, what are the real, I know the real values, they're either 0 or 1. And so the model is going to say, we're going to predict 0 if this number here is less than 0.5. So we'll predict 0 for all of these. So we have 4 things that can happen. We can actually have the training value be 0, and we can predict 0. That happened 534 times. We can have the training value be 0, and we can predict 1. That happened 20 times. So then we could have that the training value was 1, and we could predict 0. That happened 85 times. And we can have the training value is 1, and we predict 1, and that happened 61 times. So the correct predictions are the ones that are on the diagonal. The incorrect predictions are the ones that are off diagonal, right? And so perhaps most importantly, you know, from a practical matter, you want to know if you predicted 1, how well did you do? Well, if the real value was, you caught 61 of the 146 moves, but perhaps more importantly, you predicted 1 when it was actually 0 only 20 times. So of your predictions of 1, you were right 75% of the time, 60 out of 80. So this is a very useful piece of information, because depending on how important a correct prediction is, or, you know, whether you care about, you know, this and this versus, or whether you care about this or this, you know, you can see whether how good your model is. I mean, for example, if you're trying to predict if somebody has cancer, you want to make sure that, you know, you don't have many, you didn't miss many of the ones that were really one, but it varies. So, in other words, if you were just going to say, I want to predict when the when it's going to be up 1%, it actually didn't do badly. It was right about 3/4 of the time.
Professor, I mean,
Yep.
didn't it predict only 40% of the time? I mean, if the training value was 1, it predicted 0, 85, and 1 only 60 times. So it's like 40%, right?
The problem is there's 4 different ways to skin this mule, and you can either say of the times it predicted 1, what was it right, or of the times that it was 1, excuse me, which is the column, how many did it get right? So you see, so there's 2 different, it's asking 2 different statements. It's saying 2 different things.
I mean, in other words, we can say that by a random choice, you'll classify one as 350 times, 50%, because that's 700 data points. But then you will be wrong a lot more times. But here it is classifying 0 in a much better way. And then what's getting in 1 is more correct set, right, Adam?
Well, there's many ways to say it. So basically, we know that it was the value. It took the value 1 about 22% of the time.
Right.
So if you never predicted 1, you'd be right about 78% of the time. If you always predicted 1, you'd be right 22% of the time.
Right.
Whereas if you use this model to predict 1, you'd be right 3/4 of the time.
Right. Right.
Now, I'm so far from claiming that this will make you money, it's not even funny. The predictor, you know, imagine like the 3 times you were right, it was up 1%, and the time you were wrong, it was down 4%. So, you know, this is very far from making money, which is why it's reasonable that it can have such reasonable looking numbers. Okay. Now, as I said, if you want percentages, you know, you could use another function called proportion table. So you apply proportion table to table, and now it gives you the same numbers as before, but just as percentages. Yeah, so we're talking about right. You know, one of the things you can do is you could say, well, I don't care about, you know, if I predict a move isn't going to be up 1%, and it is up 1%. I only care that if I predict it's up 1%, that it really is. So as Neil said, you know, you just sort of normally predict, you know, if it's bigger than 0.5, but you can change that. You could do something like, say, if you know, I will only take my prediction if the probability is greater than 0.8, you know, and then that would give you much less times when you predict 1, but presumably, you know, you'll get a much more accurate reading. So in this last line, I just say you could use the if-else. So if you use if-else, y dot prediction greater than 0.810, this would assign 1 only to those times that the model thought there was at least an 80% chance to not move. Okay, so did I forget something? Okay, the answer is yes, I did forget something. I forgot to say, you know, that I showed you how it did with the training data, but that's not really how accurate the model is, because after all, it used that model to train. The real test of how good it's going to be is on new data. So what I need to do is not use my training data, but now that I've decided that this is the best model ever and we're all going to get rich from it, I need to test what it's going to do on new data to get a better idea. So I need to see how well it's going to predict on new data. So I use a predict function. I still have the same model, but my new data is the test data. And I'm just going to use the classification. And so I'm just going to get my prediction. I got my X data. The model tells me what to do. And it's going to see this. But now, why are the numbers different? Don't forget there's much less test data. But now we can see that it's right on if the times it predicts 1, it's slightly better than 50%, which still isn't bad. But it's notice it is significantly worse than it's gone from about 75% to 55% when it now has to look at new data it hasn't seen before. And this is so typical of what you see.
So I have a question here, Adam. So for the value of lambda, we use cross-validation, right?
Correct.
And even with cross-validation, the test results are much weaker compared to train results. Is it because we picked the smallest value of lambda, and so is that the reason?
That's not the main reason. I mean, obviously, if you took a crappy value of lambda where you weren't doing very good on the training set, you know, it might not matter whether you take new data or old data. But the main thing is that you fit the model to the data it's seen, and it's seen the training data. So it's not surprising that it does better with the training data. The whole point of, you know, and don't forget, one of the main points of from the point of view of prediction, the major point of regularization is that it doesn't allow you to make the model that's best with the data it sees. It forces it into a box where it says, no, you know, even if you want to take this really weird value to make it fit better the data you've seen, don't think that in general with new data it's going to work that way, so we're not going to do that. So this is what Niels called the bias variance trade-off. You're introducing some bias to allow much lower variance when you make predictions. So the point is in fact, you always expect your test data results to be worse, but the point of regularization is that it's allowing the difference between the two not to be as great as it would be. Or that's one of the points.
Sorry, one more question. When we do cross-validation, right, we fit on n-1 fold and then get the parameter value again on the fold which we have not used. How does cross-validation work? Can you just explain me quickly?
Sure. So if you're going to use cross-validation in the context of Lasso or Ridge, first of all, you start off with a choice of, say, 100 different possible values of lambda in a range. For each lambda, you then create 10 models. Each model is using 9/10 of the data, and then you predict on the 10th. So you have 10 estimates of the error, and you average them. So for each value of lambda, you get an estimate for the error.
Okay.
Now you do this for every value of lambda. Now you take the value of lambda, which the average estimated error is smallest.
Okay.
So if you're doing 10-fold cross-validation and your grid range of lambda was 100, you were looking at 100 lambda, you'd be producing 1,000 models.
Right.
Does that make it clearer?
Yes. So now question is, like, even when we are using cross-validation, we are estimating error on the data set which we have not seen. Correct? So
in a modified sense, I mean, you divide your data set, your training set, into 10 pieces, say, right. And the first time you leave out the first piece of data,
correct.
and you train on pieces 2 through 10.
Correct. Right, but the error is computed, like you compute the train the model on the 9 pieces, and then you estimate the error on the 10th piece, right?
Correct.
And,
yeah, that's the whole point.
And then you pick the lambda where the error from the 10th part, which is like keeps changing, is the minimum, right?
Well, well, sort of. I mean, you know, so you have 10 estimates, right?
Right.
You grade 10 models. You take the average of those.
Right.
That gives you your estimated error for that particular value of lambda. You now have 100 different estimated errors based on the 100 values of lambda.
Correct.
And so you take the lambda, which has an average estimated error.
Right.
Okay. All right. Okay, so the one thing I thought it was I should show you is remember the whole point of or a point of Lasso is it eliminates coefficients. So I actually, with this for coefficient, you can see what the coefficients are, and where these dots are, that means these were 0. So you can see in particular, and this is kind of interesting, it just only wanted one of the logs. Some of these coefficients aren't too big. It didn't like this. It's interesting, the moving averages were irrelevant. My best guess is what it's telling you is the SMA, remember, stands for smooth moving average. Is my guess is the smooth moving averages were just highly correlated with the rest of the data, and they didn't give you anything interesting. It gave some use to RSI, but nothing too big. Well, some of the momentums were okay. It liked the median. It used the median as a reasonably important indicator. But you can look at these numbers and try and make guesses. So, you know, one thing you could do is you could, you could then say, all right, I'll just use the coefficients that were non-zero and rerun the model with just those coefficients.
Also, last time we said that before running Lasso or ridge regression, we need to normalize the indicators.
Right.
We didn't do it here.
I also said last time that GlimNet does that for you.
Okay.
If you look at GlimNet, it's standard. It's a choice. You can tell, no, I don't want you to, okay, but it does automatically do that.
Can I ask a question? If it does that on the training set, what does it do on the test set? I mean, if you normalize on the training set by saying, subtracting the mean and dividing by the standard deviation, right?
Right.
But I mean, you're not allowed to do that on the test set.
You're not allowed to. Yeah, I mean, this is the standard point, right? You know that you got to use the mean and the standard deviation that you calculated from the training set, right, not rescale. No.
Right.
It takes care of that. To the best of my knowledge, I mean, I don't honestly, I didn't think about it this time, but I mean, this is the standard thing that, you know, when you predict, you have to standardize by the data you already have.
Right.
You cannot do that.
And Neil, why do you say that on the test you cannot do the normalization? Because you don't have all the data.
You don't have the data, right? So you can't compute any.
Correct. Okay.
Any mean or any standard deviation because you don't have the data. So.
Right. So you are assuming the data is stationary and the same mean and sigma will apply to the outer side.
It's not stationary.
No, well, I mean, I don't know how it works there, but in it's, I think if you look at the code that I included, there you have a scaler, so that scales the data, but so it computes the mean and the standard deviation from the training set, and then it actually uses those values to normalize the test set also.
Okay.
Yeah, so yeah, and I that's standard thing. Okay, I want to skip ahead. So my last slide is, you know, I say with Lasso, the software chooses the best lambda. With support vector machines, we'll see that there's hyperparameters that it doesn't. And I say, wouldn't it be nice if there was a package that split the data nicely, had a large number of ways to find the best parameters, compare the models side by side with whatever measure of accuracy one chose, and one might add to that, took care of all the scaling too. And I'm going to talk about that next week. And in Python is scikit-learn, and you know, standard scale will do that. Eventually it did, actually, because originally they decided that because they didn't want it to crash, they should redefine standard deviation. but they caught that bug when people, they didn't really understand it was a bug, but when enough people insisted, they changed that. But dealing with that is an important thing, and as I said, there's a package called Carrot and R that'll do it automatically. So when you just give it the Y, you give it the X, you apply a scalar to it, and it just deals with all that stuff, and you don't have to think about it. Any other questions?
Yeah, I have one question. When we pick the value of lambda, you pick the smallest value of lambda, right? And so by picking the
lambda, I gave the smallest error
of all the lambdas which came out, right? We picked the smallest. So if we would have picked like the lambda which was one standard deviation away from the smallest, the out of sample performance would have been a bit better. Expected to be a bit better.
I would imagine it'd be very similar.
Okay.
I will do that for next time.
So I'm just trying to understand what will be the guideline. Why did we not pick the lambda which gave the smallest mean error over our training set? Why did we not use that lambda?
We did. That's the smallest lambda.
That was a lambda which gave the smallest mean error? That was a lambda we picked, right?
Yeah.
Okay.
That's the one we used.
Okay.
Yeah. So I think, so this idea of using the one that's within one standard deviation of the best value, but it's the simplest. This goes back, as far as I know, to literally Leo Breiman and his book on trees. And there they had a much more serious problem with overfitting. Trees, notoriously overfit without the correct kind of pruning. So doing things like this, picking not the simplest model, but the simplest model, not the simplest model within one standard deviation of the smallest error, had some real traction. How to put it? It doesn't. I think you're better off. I think you're better off just sticking with something that makes sort of statistical sense. I mean, and that is to just take the smallest one, and not if the models are that noisy where you really shouldn't be taking the smallest one. Probably need a better model.
Right. So again, one question here, like even we did Lasso, still there was some kind of, we ended up doing some kind of overfit because out of sample results were weaker than in sample results, because if we would have done correct fit, then we would have seen out of sample performance similar to in sample performance, right? So no matter what we are doing, we are still ending up with some kind of overfit.
I mean, it's the nature of the game, but I mean, it's the nature of the game that the model is always going to do better on data that was used to train the model.
Right.
The idea of using the regularization is to reduce the overfitting.
Okay.
To, not allow it to completely just use the data to apply these constraints. And the fact that we choose the lambda that does the best for predicting is,
right.
It makes that a very reasonable thing to do.
Right. So I think it will be really interesting to see some using this kind of data and just running a linear OLS versus lasso regression, and to see like how much it is improving in terms of overfitting. What an OLS will give.
Next week, yeah. It
will be really good to see in practice. Yeah.
So I did want to give a little homework. It's not hard and it's very open-handed. So we saw this model was okay and not great. So my question is, how could you improve this model? So if you could come up with 5 ideas, maybe we want to go back 10 days.
Yeah.
Maybe we want to not, maybe we want to not use logarithms. So come up with, 5 suggestions and see if you can implement one.
Yeah, I think one.
They should send me the code.
I'll definitely try. I think one idea could be that we can take the beta times market move from these returns, so then probably predictability will be a bit better.
Right. Another thing might be to take polynomial terms to allow interactions.
Right.
But looking at more days, you know, there's various things. I mean, but just have fun.
Yeah.
And if people have problems or want to have code questions, just send me emails. I'll solve them.
I'm definitely going to try this, Adam, and I'll give you feedback on this.
Okay.
All right. Okay. I'll send you some questions, because if I have trouble running this code on multiple tickers, then I'll ask you a question at how to do it.
Okay.
Right. Any question, Tejas, Vijay?
Not right now. I guess I will go to the material and then hopefully I will drop an email.
Yeah. Okay. All right. Thank you very much, Niels, Adam.
Okay.
Adam, I still see you have boxes. You have not unpacked all the boxes yet.
This class could be going till next year, and you'll be able to make that statement.
It's just a prop, isn't it?
Yeah. I will tell you this. I was kind of seriously thinking that within a year from now or so, I would be on my way to someplace like Seattle with a better climate. Mm-hmm. After all this work and effort and aggravation, I ain't moving quite so easily.
Well, take some pictures of it. So whenever you feel like moving, just look at the pictures, and you will realize what a mess it is. So.
Yeah.
In the middle of winter, Chicago, it can be very, very tempting to move to Seattle. That's for sure.
You need to build a model with global warming inputs to see whether weather will be stable in future. By the time you get to Seattle, it may be bad there.
You see, I'll tell you,
maybe underwater.
The good thing for me is that I'm no longer interested in climate. I'm too old. I'm just interested in temperature, and for that, it's just fine, whatever it is, wherever it is.
Yeah, and I'm not sure if that's going to help. I was listening on NPR that I think the Seattle is probably the #1 city with the worst air quality right now.
Really?
Because of all the fires and everything. Yeah, the visibility is so low. I mean, it's been rated even worse than Delhi.
that's saying something.
Yes.
So we need
worse than Beijing.
Oh, worse than Delhi. I mean, I think this year because of all the fires that they were having in the forest.
That's the feature with the highest weight, Adam.
Well, look at the bright side. You can always toast marshmallows.
In the smoke, I don't think so. Marshmallows.
A little closer.
You can smoke fish, that's for sure. You can just.
There you go.
Just hang it outside.
They have great salmon out there.
Smoked salmon, that's right. There you go.
All right. Thank you. It was an excellent class.
Yeah.
Great class.
Thank you.
Lot of
input. Thank you, Adam. Thank you.
Thank you. Good night.
Good night.
Good night.
See you next week.
Yes.